Welcome to week 6 Q&A. So talking about what's coming up, we have your last quiz tomorrow, quiz 6, and that's going to be over the chapter on enols and enolate chemistry. So make sure you do your POGLs 23A, B, and C and turn those in. You also have online homework over these chapters. I think it's chapter 22 in your book for sapling. So you have that, and I would do that. And then I did give you a lot of biological information because those are the last few chapters. But I just want to tell you your final exam, the is cumulative. It's really going to mostly end on the chapter information that you're going to see on your quiz tomorrow. So it's going to be from Organic 1 material. So writing Lewis structures, informal charges, resonance structures, acid-base chemistry, stereochemistry, the alkenes, electrophilic addition, and so that's a lot of Organic 1. You'll probably have about 5 naming questions, so practice some of the naming chapters and your priorities in naming. And then you'll have about 5 questions on spectroscopy, so you can review that. So that's 10 questions right there. And then out of the 40, 20 is going to come from the Organic 1, and then 20 is going to come from Organic 2. So be sure to review your topics. This is a 200-point exam, and it can replace your lowest exam, either 1, 2, or 3, based on the percentage. And it is all multiple choice. The other thing that we have out, I think we're at like 68% response rate for the evaluation. So if we, and I don't get those until like late August, so no worries there, but I do need your feedback because it's going to help me design this course and make it better for those coming forward. But I need to get about 75% response rate. And then what I do is, like, if someone is, let's say you're 68.2%, then I will round that up to 69.2%. And you see how that could all of a sudden become closer to a 70%, which is a C. So that really does do well to help each other out, and that you're contributing as a class as a whole. Okay, and then there's the exam wrapper, and there was questions on the announcement, and I basically am going to add a 5-point bonus to your final exam score. So that's also going to help you out. A couple of people have already turned that in, and you'll see that. All right, so let's go over today. We're going to go over your exam 3. All right, so here the first one you were to work out a synthesis. So this is the open response. And what you need to see is, and everybody did really well on this. Okay, what you need to see was this was an alkene, and I said you need to go through an amine. So you had to have an intermediate that was amine, and you're starting with an alcohol. So in your knowledge of reactions, you need to convert the alcohol to an amine, and then from the amine you can do an alkene. So you know this is Hofmann elimination, and this is the excess iodomethane, and then you treat it with silver oxide, water, and heat, and that gives you elimination. So the amine here, to go to an amine, you can convert it to a leaving group like PBr3, and then you could do the Gabriel synthesis, which is not actually preferred because you would want a primary amine. You could react it with sodium azide, and then you could do lithium aluminum hydride. And then, of course, you have to treat that with acid. So let's just do those reagents and see what that would do. And I expect you to draw all of these out. So PBr3 converts an alcohol to a leaving group, because alcohols are horrible leaving groups, so that's organic earlier. Okay, and then this is an SN2 reaction. So we have this, and then we get the azide. And 3. Now I would like for you, when you're drawing out your reactions, of course, you're not going to be doing this anymore because, except for your quiz, you won't have any other open response. But I like for you to draw out all the Lewis structure. Okay, so that's an SN2 reaction, and then lithium aluminum hydride, and then you work it up with some acidic water, and you get, actually you would get, which wouldn't matter because stereochemistry there won't matter because it's going to be a CH2 NH. Actually, that would be NH2. All right. And then what happens? We are at this point, because we have our amine, and you react those reagents in, and you get your product. Okay, so going on to problem number 2. Okay, this problem asks for step 2 to show the reaction mechanism. So I didn't ask for the first reaction mechanism for step 1, and that is a cyclohexane. Make sure you always take the time to check your structures and count your carbons. Okay, so thionyl chloride and pyridine. Okay, so pyridine is this structure. When you ask for reaction mechanisms, you want to show your structures, your Lewis structures. So there's your, now this converts an acid, carboxylic acid, to an acid chloride. And you can just do that. Some people gave the reaction mechanism. That's fine. But then we have this here, and what I want you to show here is this is nucleophilic acyl substitution. So it's a mechanism that you are expected to know in organic chemistry too. So I need to see that you can draw these 2 electron flow arrows. I need to see that you can draw the tetrahedral intermediate. So I needed to see this. And we don't take shortcuts on mechanisms that I need to see. So this is neutral, this is neutral, this is neutral, intermediate. Now we, you could deprotonate the nitrogen, or you can just deprotonate it afterwards. So the Cl is a good leaving group. You want to reform the carbonyl, so that's the driving force, and whether you have the leaving group before or after doesn't matter to me. And basically, you could either use pyridine, I'd be okay with that, or the amine, or you could even use water, okay? Because you could do this in a workup. Most time in all of organic chemistry, you do a workup, but I just want to see that you deprotonate. You have a deprotonation step, and this gives you an amide. Okay, so what I want to see is that you can convert a carboxylic acid to an amide. Okay, that was one of the objectives you needed to understand. Let's go on to question number 3. Question number 3, it says use the Gabriel synthesis. So you needed to first use the Gabriel synthesis. Gabriel synthesis is great for making primary amines. So we're going to make the primary amine here. And it says use the Gabriel. So Gabriel uses the potassium thioimide. And you can actually buy this. So you can buy that. And it says draw the reaction mechanisms for both reactions below. And so a lot of people did the hydrazine too. So I just wanted to see that you know that this is an SN2 reaction. So what I really wanted to see was you showing the reaction arrows there. And so we have 1, 2 carbons, and then you have the nitrogen here. I wasn't concerned about the hydrogenolysis reaction. I wasn't concerned about that reaction mechanism, so I'm not going to go through that. But some people showed it, some people didn't. Okay, so there's your, we haven't started with your starting amine yet, right? Because then after hydrazine, you get the primary amine. So I needed to see that. And then it even tells you to do the secondary amine by reductive amination. Okay, reductive amination, you have to use a ketone or an aldehyde. So we got to look at what amine you wanted. It's a secondary amine. So we have, okay, so this is a primary amine, this is a secondary amine. And that means we need this portion here to be a ketone. So there's your ketone. And then when you do these, you have a weak electrophile and a weak nucleophile, so you need to have a little bit of acid. And I really care about that when you're doing reaction mechanisms because you have to show the reaction mechanism, so you need to have that. And then you reduce that. You can do lithium aluminum hydride, or you can do something a little more milder like sodium borohydride. So let's look at that reaction mechanism. And the reason why that reaction mechanism was called for is because that's a reaction mechanism you're expected to know. We made an amine in the last chapter. So what happens here? The first thing that happens is you always protonate the carbonyl. And so I needed to see that for full credit on this mechanism because this is a weak electrophile and now it's a strong electrophile. Now we have our amine now that can attack the carbonyl carbon. And so now we have the electron flow arrows showing you that we have a tetrahedral intermediate. Okay, and nitrogen here has, I didn't do that right, so give some space here. So here's our nitrogen, and then nitrogen, and nitrogen still has 2 hydrogens. So I wanted to see that you can recognize that you need a formal charge there, and then that's the water now, because this became water, will deprotonate. A lot of people try to make shortcuts on this. When I ask for a mechanism and I'm looking for a particular mechanism that I think you need to know, you're going to lose points if you don't show all the deprotonation and protonation. So why is this important? This is your hemiaminal. Hemiaminal. All right, now what happens? We're going to the amine. Okay, so we got to lose water. And so we're going to protonate the OH because we need that to be a leading group. And you need to show that. All right, and now you can have that leaving group there, and that leaves there. And And do you see that that has a positive charge because nitrogen has 4 bonds, and then the water will deprotonate that to generate your catalytic acid back, and you have your amine. And that was really the mechanism that I needed to see that you knew how to do, reinforce that. And then, of course, sodium cyanoborohydride is a hydride, and the hydride will actually attack the carbon here. And you didn't have to do this mechanism. Some people chose to and some people didn't, but I didn't take points off either way. And then this would get protonated usually by a little water workup. And you do a separatory funnel and you get your secondary amine, and that is reductive amination. And then our fourth one. The fourth one, each reaction, and you need to draw the reaction mechanism. All right, so here we have an alcohol, and we need to make a primary amine. Now, to do this, you could convert this to a leading group, and you can use sodium azide, and then you could reduce that with lithium aluminum hydride. And for sodium azide, you do have to use lithium aluminum hydride, and then that's one way to do that. You cannot use potassium cyanide, people, because you're adding an extra carbon. You see that carbon? So if you count here, you have 5, 6, 7 carbons, and here you have 7 carbons. So if you had 8 carbons, then you would want to use like potassium or sodium cyanide. Okay, this is an SN2. Gabriel, anytime you have a primary amine, Gabriel's great. So you could either do tosyl chloride, pyridine, or you could use PBr3. If you did like HCl and HBr, we've talked about that in the alcohol chapters. That's not the preferred way to convert your alcohols to alkyl halides. They give you low yields. So you didn't get full credit for that if you chose that. If you try to do alkylations with ammonia, low yields, I've talked about that. That's not the preferred way. So I need to see, Gabriel synthesis or one of these preferred synthetic routes. Gabriel synthesis, so yeah, we do the diamide, and I'm not going to go through these reaction mechanisms here for time. And then hydrazine and heat, and that would give you that. So those are pretty much the two ways that you needed to do. And then, of course, the next one, you could have done, you're dealing with a secondary amine, so you could have done reductive amination. Okay, so if you have that amine, so this would come from an aldehyde. So if you want to do reductive amination, you need a little bit of acid there, and then sodium cyanoborohydride would work. That would be reductive amination, or you could do nucleophilic acyl substitution. And what that would be is you'd have to react it with an acid chloride. Okay, so you react that amine with an acid chloride, so what do you get? Let's just go ahead and draw that out. Okay, so you would get this, and then you can reduce that with lithium aluminum hydride, and then you might want to add some acid, and that would reduce that off to give you your secondary amine. So the two ways to make secondary and tertiary amines are reductive amination, are your best bet, or nucleophilic acyl substitution followed by reduction. Okay, the next one, everybody did pretty well on this one, and it's just recognizing your materials. I've given you feedback on that, so I'm not going to go over those. Everybody seemed to do well on that. Okay, let's go to your sapling. And you log into sapling here. we will go over your exam 3. Okay. Now, so you had multiple choice questions. You had about 25 of them. Classification. I think everybody got that pretty well, but I'll go through it. So you wanted a primary amine. So how do you classify your amine? You find the nitrogen and you say how many carbons are attached, and it's attached to 1 carbon, so that makes it a primary. Ranking. You have to rank the basicity, so you want the most basic first, most basic to the least basic, and out of that, just your aliphatic amine, because they have electron donating groups, so this is going to be your most basic, and then ammonia will be next. Okay, there's no electron, so this has electron donating groups, this has no electron donating groups. And then, but those are still going to be more basic than an aromatic amine. So the next one's going to be pyridine. This is pyridine, and this is an aromatic amine. And the least basic is pyrrole. And we've talked about pyrrole because once you, so you have 6 pi electrons here, so this is aromatic. And once you protonate that, so let's just show what that looks like protonated. This was actually in your POGL. And the problem with that, now you have 4 pi electrons, and this is anti-aromatic. Okay, so that is your least basic. The next one, predict reagent. Okay, you've seen this kind of over and over, I guess, making primary amines. Let's look at this. We have an alcohol, and we are making a primary amine. But notice we have 6 carbons, and here we have 5, 6, 7 carbons. So we have to add a carbon. So you need a reagent with potassium cyanide. You also have sodium cyanide. You have to convert the OH to a good leaving group. I see that you can do that with PBr3 of these reagents or tolusyl chloride pyridine. Either one of these will work. But with cyanide, what you're going to get is you're going to get this, and then you're going to have to reduce this with lithium aluminum hydride. So that's why you got to get that reagent in there, lithium aluminum hydride and H3O+, and that kind of separates those two here. So those are the 3. You have tolusyl chloride, KCN, and then sodium borohydride. Predict starting material. Okay, predicting starting material. This is reductive amination. So you need to be able to see that. How do you know that? Well, classify your amine. You have a tertiary amine, and you're reacting it with an amine. So you're reacting with an amine, and then you're doing lithium aluminum hydride and water. So this portion here comes from here. And I drew that wrong, so let me just, okay, so there's that. So a ketone would work. And that was also one of your questions. So ketone would be, you either reductive amination, the starting material is either ketone or aldehyde. And remember, it goes through the amine and then you reduce the amine. Okay, predicting product. this one, lithium aluminum hydride and water, we'll reduce that to the amine. So what you want to do is you also want to count your carbon. So how many carbons do you have here? 6, 7, 8 carbons. 6, 7, 8 carbons. So you want to make sure you have 8 carbons. That's a reduction. Another predict product. This is elimination. So this is probably one of the first reactions you worked on in this chapter, silver oxide, water, and heat. And you've worked the mechanism here. The first step, you're going to get over-alkylation. And then the second step, you're going to get, there's your alpha. You're going to get, this is a Hoffman leaving group. So this OH is going to choose the beta hydrogen. That's going to give you the least substituted product, which is a Hoffman elimination. So if you chose this Zatsev's, the more substituted, it would have been wrong. Predict starting material here. Okay, this is nucleophilic acyl substitution. Do you see that? So how do I recognize that that's nucleophilic acyl substitution? Do you see the carbonyl there? So this CH3, CH2, NH2, and pyridine. So this is the nitrogen. This is this one here. So the pyridine soaks up the HCl that's formed from the acid chloride. So this portion here would come from an acid chloride. And so that's what you look for. Notice I do all that before I even start looking at the options. Now, the reason why amides are the least reactive. So if you've looked at the carboxylic acid derivatives, they're the least reactive. The acid chlorides are the most reactive. So you can go from a most reactive to a least reactive. Carboxylic acids are least reactive with amides, so neither one of those will convert without going through the acid chloride. Reaction sequence. All right. So here we have toluene, and we're trying to make a para-substituted nitrile. Now, in order to install nitrile, because we've done these aromatic substitution reactions, the electrophilic aromatic substitution, remember E's, and this has to go through the arene diazonium salt, okay, and then this is called a Sandmeyer. So if you've done your reading, you know that that's a Sandmeyer. So that's a copper cyanide reagent once you get this reagent. And so how do you get this? Well, you have to go through an amine. So this has to get an amine there. And then when you have the amine, then you can do sodium nitrite and HCl. So and then you can do the copper cyanide. So how do you get to the amine? Well, you'd have to do a nitration. So that's nitric acid and sulfuric acid. And that gives you the nitro. And then you reduce that with zinc, mercury, HCl. And that will give you the aromatic aniline. And then the sodium nitrite and HCl will give you the great leading group, the N2, and copper cyanide will give you the product. Predict product here. All right, so here we have an ester, and the thing you're learning here is, are esters, what kind of, are they activating? Are they deactivating? What kind of leaving group? And then we have sodium hydroxide. So let's do the first reaction. So you know that your electrophile is the Cl plus, and then we have an ester, and the ester is electron withdrawing group, so that's going to be deactivating, and we know deactivating is a meta director. So that means that we're going to get the Cl added to the meta position. So once you do that, you add your Cl. That already eliminates a couple of the questions. And then sodium hydroxide here, this is saponification. So if you have an ester with sodium hydroxide, then this goes up here. I will do this mechanism real quick. And we know that the esters are good leaving groups. We learned this early on when we were doing the Grignards, the very first week in this course. And that is OH, but you're in a basic solution, and this is a carboxylic acid. So you're going to deprotonate that acidic proton, and this will be your answer. Oh, don't forget the chlorine, folks, on the meta position. That is your answer. All right, so we're halfway there almost. Okay, so these are just, do you know your reactions, your reagents? So here you have an acid, carboxylic acid, and how would you convert that to an acid chloride? And those reagents is thionyl chloride. So that is just, do you know? Okay, ranking. Here we're ranking carboxylic acids. Now carboxylic acids, the acidity is the opposite of basicity. So what does that mean? That means if you have electron withdrawing groups rather than electron donating groups, that's going to make it stronger. So like this one here, fluorine is your most electronegative electron withdrawing groups. So when you deprotonate with a base, that OH, anything that pulls that electron density away, so it pulls it away, is going to be more acidic. So this is going to be your most acidic because you've got 3 electron withdrawing groups, and you don't get more electron withdrawing than fluorine. This one has 1, so this is your most acidic. This would be your second. And then here you have chlorine, and chlorine's electron withdrawing compared to none. So this would be your least. Okay, now we're doing reaction sequence. And some of this stuff is a little review too, to kind of prepare you. So I can tell you right now, you still have an aldehyde in your product. So we're going to have to do some protecting group chemistry here. Okay. So I can tell you right now that you're going to have to protect this aldehyde in order to do reactions on the ketone, because the aldehyde is about 10,000 times more reactive than a ketone. So you're going to have to protect that. So do you remember the acetal chapter? So how do you protect that as an acetal? You add the tosic acid, and you add the ethylene glycol. Okay, so that's your first reaction. You have 2 reagents to do that. If you just go straight in with a Grignard, then it's going to react with the aldehyde first. And now you can take the Grignard, because the Grignard's adding, you're going from a ketone to a tertiary alcohol. And you should think Grignard. So this is your methyl magnesium bromide. There's your Grignard, and then when you add H3O plus, then that's going to hydrolyze your acetal to give you back your aldehyde. Okay, this is predicting your starting material. And you have lots of reactions there, so let's see what's going on. A lot of times it's just a matter of recognizing. Okay, so you have a secondary amine. So I'm telling you right now, you should be thinking either reductive amination, or you should be thinking nucleophilic acyl substitution, followed by reduction. And so here you have thionyl chloride. Okay, well that can convert an alcohol to an alkyl halide, and it can convert a carboxylic acid to an acid chloride. And the second thing is the amine. All right, so right there, you're not dealing with a ketone or an aldehyde. So what's the starting material for reductive amination? Either an aldehyde or a ketone. So we're definitely going to do the nucleophilic acyl substitution. So that tells you right there you need to have a carboxylic acid, and then this CH3 nitrogen is this right here. And so, and then you reduce lithium aluminum hydride and water, or acidic. There's your carboxylic acid. Which starting material would most easily be converted to the amide through nucleophilic acyl substitution? Okay, so how would you make this amide? And the key here is most easily. And I can tell you right now it'd be an acid chloride or an acid anhydride. Most easily means you don't need any acid. So an acid anhydride out of the carboxylic acid derivatives are the most reactive. These are very reactive, and carboxylic acid would not, and aldehyde would not. So this is actually the option, so you can take that. Okay, predict reagents. Okay, here we have ketone and a carboxylic acid, and we're trying to make an amide. Okay, so obviously you need to convert this to an acid chloride because this is an amide. So this is thionyl chloride, and you add pyridine to soak up the HCl, and then you add your methylamine. Predict starting material. Okay, sometimes you want to be able to convert these Lewis structures, these condensed formulas into Lewis structures, and figure out what the reaction is from there. So that's why this is a good one here. What is the starting material to synthesize? And you have CH3 to CH, CO2, CH3. I want you to convert that to a line drawing, okay? So now you should be able to see, so this is CO2, CO2, this is your CH3, and this is CH, and then this is the CH3 here. So there is your line drawing. Now you can see, oh, that's an ester, and you're making the ester, so synthesize means that's your product. A solution of methanol, so a solution of methanol, and catalytic sulfuric acid. So this is Fischer esterification. It's very important. And so Fischer esterification requires a carboxylic acid and an alcohol and catalytic sulfuric acid or some kind of catalytic acid. So then you have to choose, and you have to say, okay, there's my CH3 this is my CH, and then this is my CO2H. And then you can go and look. If you had to, you would draw each one of those out. I see that we have an alcohol, an aldehyde, and an amide. So you definitely want to count your carbons. Okay, we've done that one. We are on 18. All right, so what is the major product in the following reaction? All right, this one, I see that we have an ester. So you always want to kind of say, what do we have here? We have an ester, and we have a Grignard. Okay, so you've seen this a lot by now. So we're adding 2 carbons there. So this is going to come here, this is going to go up, this is going to be a leaving group. All right, so here, let's do this real quick. This comes, you can do, this goes up and this comes down. I don't normally tell, that's more advanced when you're first starting. You don't really need to have that many electron flow arrows because a lot of times you don't know what you're doing, but you are telling a story. All right, this is a ketone. Ketones are more reactive than starting esters, so you're going to have another. So you should know by now, and then it gets protonated, that esters and Grignards make tertiary alcohols. So you can go and look for the tertiary alcohol there. All right, this one is a predict the product. Here we have an ester, ethyl ester dibal. Okay, so if you study your reagents, you would know that dibal is mild and will reduce an ester to an aldehyde. So it's just going to add 1 hydride, and this is going to come up, and that's going to leave, and that's going to give you an aldehyde. And dibal is diisopropyl or diisobutyl aluminum hydride. Okay, so it only delivers 1 H minus. Usually you also do this about minus 78 degrees. Anytime you're using dibal, you want to do it very low temperature. Okay, predicting reagents here. We have an ester, and we are making a carboxylic acid. So when you convert an ester to carboxylic acid, this is called saponification. You can do it with heat and acid, but it's so much easier just to do it with base and heat. Okay, lithium aluminum hydride, that's one of your options. We give you a primary alcohol, lithium aluminum hydride. And that is the only reagent that would do anything other than the sodium hydroxide. Okay, predict product here. This is a good one. So you take an acid chloride and an acid chloride with copper reagent. So copper, lithium. Okay, copper, lithium will deliver just 1. Okay, so this will give you a ketone. And that is what's nice, other than a Grignard. A Grignard would go all the way to the tertiary alcohol. This is called a cuprate reagent, and they can deliver just 1 alkyl group. So there's your answer. You get a ketone. Okay, the next one, predict the product. Now, this one does not have a reducing agent. You just have the one reagent. So it's going to make an imine. So we lose water. So we're going to lose this H2, and we're going to lose that oxygen. And we're going to make the imine. So it's just the imine. You do not reduce it if you don't have sodium or cyanoborohydride or lithium aluminum hydride. Okay. A few more here. This is, you have aniline. And we have to predict the reagents here. You're going to convert that to an amide and a nitro group. So do you recognize that aniline is an activator and therefore is an ortho-pair director? So we can go ahead and add sulfuric acid and nitric acid, because that will give you the NO2 there. So that would give you NH2 nitroaniline. And then how would you convert that? And the best way to do that is an acid chloride with pyridine. Could you do it the other way around? Yes, you could, because so you could do this first and this second if you wanted, and that's because you still have a lone pair there. Okay, so if this had been something like this, which we could call it, a reverse amide, then this would be a meta director. But this, because of the lone pair, is an ortho-pair director. All right, and now we have two more. Two more on this assessment. And we have to pick the reagents on this. So we have an ester, and we are trying to make an alkene. And right off the bat, I'm thinking the best way to do this is a Wittig reagent. And so this would come from something like this, right? So this carbon here would be this carbon. And then what does a Wittig need? A Wittig would need an aldehyde or a ketone. So this carbon here would be an aldehyde. So, but the problem is we have an ester. How do you go from an ester to an aldehyde? And that is dibal. So dibal would take that ester to an aldehyde, and then the Wittig would give you an alkene. The last one, what is the major product in the following reaction? Well, we have toluene and potassium permanganate does benzylic oxidation. Benzylic oxidation, so it will convert that methyl group to a carboxylic acid. And then the second thing, we have thionyl chloride, so that will convert that carboxylic acid to an acid chloride. And then we have dibal, and dibal will make that an aldehyde. And you can see how aldehydes are really helpful because you can convert them to a lot of things. So aldehyde would be your product. Okay, that takes care of your reactions on your assessment. Um, I am curious to see if we had any particular questions over content material by email. Um, so I have one question. Will there be an open response section for the final? No, there will not be. It's just going to be 50 multiple choice questions. At this point, I just do the open response to see if you know how to do electron flow arrows, recognize nucleophiles and electrophiles, and stuff like that. So I did open up the final exam for 6 a.m. So if people want to do that earlier, they can. You can send in your exam wrapper. I do have a question about the Claisian. Okay, so I guess that's the only other question I have about the Claisian, which is a good question. So let's see what that question is. I have a question about how you did your Claisian mechanism with a ketone and an ester. I was wondering how you got the second, because when I got one, it was removed when the carbonyl was reformed. Okay, now I'm not sure exactly what question this is, but we can talk about the Claisian. So the Claisian mechanism is an ester. So if you have an ester, it can be a methyl ester, an ethyl ester. One of the things you need to do is you need to, if it's a methyl, you would want to do like sodium methoxide so you don't get transesterification. With a ketone, an ester. So if we did this with a ketone, so let's say we have this ketone here. Now you've got to think about the pKa values. So this is an alpha hydrogen, and here we have an alpha. So you always want to identify your alpha hydrogens. Now you want to look at your pKa values, and the pKa value for your ketone is going to be about, I think, about 5 orders of magnitude more acidic. So you can look those up. I don't have my books right now with me, so but you can look up and find the pKa values exactly for that. And the lowest pKa value would be the one that's going to get abstracted and form the enolate. So, and here we have 2 of them. So let's just pick any one of them. Okay. So here we have what I would call my monkey face. That's going to be my alpha carbon. And then this is going to be my nucleophile. And then this is going to be my electrophile. And so then this is going to come here and attack there. And the mechanism will form a tetrahedral intermediate. OCH3, and then we have this. I gotta count 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so we've made, we have the alpha here, and this is our beta. And then with a Claisian, this is a leaving group, so this will reform. It's very different than the aldol. So that will leave, and you will get 1, 2, 3. Okay, you'll get this. So when you have a Claisian, you get a beta keto carbonyl. And so this is your alpha and this is your beta. And so if you're working backwards, that's the line you would draw. I did take off several points on people's Pogles if you didn't label alpha and beta and draw your line. So for those of you who have not submitted that, that's a heads up for your Pogle. I want to see the alpha, beta, and draw your line, because then you can work backwards. Whereas you just take your alpha here and you're like, okay, that's that. You just draw it the same way. And then your beta here, if it's a ketone, then you're like, well, it has to be an ester because it has to have a leaving group. So it has to be an ester. And so then the mechanism here would be your alpha, and it attacks there. Now, and this comes back down and that leaves. If this had been an unsaturated, something like this, then you could say, okay, well, here's my alpha and here's my beta. You draw your line and you see that that must have come from an aldol. And so that means you draw your alpha the same way. Okay, so your alpha is the same, because that's going to be there. And then your beta has to be an aldehyde. Okay, not an ester, because then what happens is you don't have a leaving group. So this is the difference between Claisian and so there's your alpha and there's your beta, and then that gets protonated actually in water. And then you also have learned that with heat that will eliminate. And then that eliminates to give you the alpha beta unsaturated carbonyl. So when you get an alpha beta unsaturated carbonyl, it had to come from an aldehyde or a ketone. But if you have a keto group, I will highlight here, if you have this beta keto group, then you know it had to come from an ester. And that wraps up the questions.